In this video, I am going to derive a formula for numerical aperture of an optical fiber. Numerical aperture is a very important parameter of an optical fiber. It is also known as the figure of merit of an optical fiber. Now, in order to find out the formula, I am assuming here an optical fiber. Let me assume that this fiber is made up of glass having refractive index N1 for the core. The core is the innermost part of an optical fiber, which is responsible for the transmission of light in the fiber. And here I am assuming that this dotted line is representing the core axis, an imaginary line which passes through the center of the fiber. And this is the fiber edge. This is the fiber edge. This diagram shows an optical fiber lying in the air, and I'm assuming that this core region of the fiber is surrounded by cladding on both the sides. And as a notation, the refractive index of the core is N1 and the refractive index of cladding on both the sides is N2. Here I am assuming that the fiber is lying in the air, that is the rarer medium. This is the rarer medium, air, having refractive index N0, and let me assume that this light ray or incident ray, let's say ray P, it is making an angle theta 0 with the fiber core axis, okay, in such a way that this angle lies in the acceptance cone, and once it enters into the fiber, since the light ray is being launched from the rarer medium and it is entering into the comparatively denser medium, because core is a denser medium. Core is made up of glass, or sometimes it is made up of plastic polymers, so which is a denser medium as compared to the air. So once the light ray goes from the rarer medium to the denser medium, according to the law of bending or refraction, the light ray will be bending towards, a little towards the normal. So here this core axis is acting as a normal or perpendicular. So certainly let us assume that this is making an angle theta 1 with the core axis. So this angle theta 1 is slightly less than theta 0, since the bending of the light has taken place towards the normal or this core axis. So it is bending towards this, okay. And once it strikes the core cladding boundary, this is the core cladding boundary or interface. So once it strikes the core cladding boundary, let me assume that this is making an angle phi with the boundary. Again, I have assumed a normal here, okay. So let me assume that it entered at point A into the fiber, and normal I have drawn at point B, and I have assumed that this normal is at angle C, which is 90 degree, okay. Now I have assumed that this light ray, once it enters into the fiber, it shows the total internal reflection mechanism, that is TIR, okay. So I am assuming that this light ray is showing TIR. This is totally internally reflected light ray. Alright. Now, according to the Snell's law, I am applying the Snell's law at point A. Snell's law is the law which relates the refractive indices of two different medias and their angle of incidence and the angle of refraction. So here at point A, it is given as N0 sine theta 0 is equal to N1 sine theta 1. So let me take it as equation number 1. Now, since I have assumed that once it enters into the core medium, it is striking the core cladding boundary at angle phi. So assuming this triangle, I am separately taking this triangle ABC for the better understanding. So let me assume this is angle theta 1, this is angle phi, and this is 90 degree angle, okay. So in triangle ABC, angle theta 1 is equal to 90 minus angle phi, right? Because the sum of all the three angles of a triangle is 180 degrees. So if this is already 90 degree, angle C is already 90. So sum of the remaining two angles, that is theta 1 and phi, is 90 degrees. So theta 1 becomes equal to 90 minus phi. Okay. So sine of theta 1 will be equal to sine of 90 minus phi. So sine 90 minus theta is cos theta, so it becomes cos of phi. So I am putting this sine of theta 1 in equation number 1. Alright, so I get sine of equation number 1 becomes n naught sine theta 0 is equal to n1. Instead of sine theta 1, I am replacing it by cos of phi. Okay. Now, according to the trigonometric relation, cos square of theta is equal to sine 1 minus sine square theta. So similarly, cos square of phi will be equal to 1 minus sine square phi. Okay. Or I can also say that cos of phi will be equal to square root of 1 minus sine square phi. So I am putting it in the above equation, that is equation number 2. Therefore equation 2 becomes n naught sine theta naught is equal to n1 into square root of, instead of cos of phi, I am writing 1 minus sine square of phi. Take this as equation number 3. Okay. Now I can also write it as sine of theta 0 is equal to n1 upon n0 into 1 minus sine square phi. Okay. Now, as long as we know that the total internal reflection mechanism in an optical fiber happens only when the angle at which the incident ray, once it enters into the optical fiber and it strikes the core cladding boundary, the TIR will happen only in case the angle phi is at least equal to or greater than the critical angle. And in case this phi is less than the critical angle phi c, the total internal reflection mechanism is not going to happen, and this light ray which is launched into the fiber, it gets eventually lost into the cladding. So it gets bent into the cladding region, and it becomes a waste. Okay, it does not show the TIR, that is total internal reflection mechanism, and it cannot be transmitted to the other end of the fiber or the destination end of the fiber. Alright, so here, in order that the light should travel into the fiber, I am assuming here that this angle phi is at least equal to phi c, assuming that it is a limiting case. Okay, and in case of in the limiting case, the angle theta 0 will be also equal to the acceptance angle, that is theta a. So I have assumed here the limiting case of refraction. Okay, so I can make these changes, that phi is equal to phi c and theta naught is equal to theta a in my specific, in this case, because I am assuming that the light ray here is showing the total internal reflection. So equation number 4 can be rewritten as sine of theta a is equal to n1 upon n0 into 1 minus sine square of phi c. Also we know that sine of phi c can be written as sine of phi c, that means critical angle is given as n2 upon n1. Okay, n2 is, it is the ratio of sine of the critical angle is the ratio of the refractive index of the rarer medium, that is here it is cladding, upon the refractive index of the denser medium, that is the core. Okay, so I am replacing sine of phi c in the above equation as n2 upon n1. Okay. So equation number 5, equation 5 becomes, equation 5 was sine of theta 0 is equal to n1 upon n0 into 1 minus sine square phi c. Okay, so theta, instead of theta it was theta a. So sine of theta a is equal to n1 upon n0 into 1 minus sine of phi c की जगह पे I am replacing it by n2 upon n1. Okay, so it is square of n2 upon n1. So solving it further gives me n1 upon n naught into square root of n1 square minus n2 square upon n1. I'm writing n1 out of the square root. So it was square otherwise, so it gets cancelled here. Okay. So sine of the acceptance angle theta A becomes equal to 1 upon n naught into square root of n1 square minus n2 square. Since we have assumed that the fiber is in air, so n naught in this case is 1. So I can write sine of acceptance angle is equal to square root of n1 square minus n2 square. Now this parameter sine of the acceptance angle is nothing but it is the numerical aperture of a given fiber. Okay. So this is very important relation. Sine of the acceptance angle is given by this relation square root of n1 square minus n2 square. Now let us say I want to find out the maximum acceptance angle or the maximum value of the external incident angle for which the light ray will propagate inside the fiber. So that can be also given as acceptance angle theta of acceptance theta max can be given as sine inverse of n1 square minus n2 square. Okay. Now there is one more parameter which is called as the delta. Okay. Delta is called as index contrast of an optical fiber, or it is also called as the relative refractive index difference. This is also known as relative refractive index difference. And the formula for delta is n1 square minus n2 square upon twice of n1 square. Alright. So this can also be written as a square minus b square is a plus b into a minus b. So same way I can write it as n1 square minus n2 square is equal to n1 minus n2 into n1 plus n2 upon twice of n1 square. Okay. Now since n1 is approximately equal to n2, I told you that the refractive index of the core is slightly more than n2. It is not exactly equal to n2, but it is slightly more. The difference is very less. Okay. So I can assume that they are approximately equal. So I can accordingly write delta is equal to, not exactly equal to, in fact it is approximately equal to. So it is the sign of approximation. It is equal to, approximately equal to n1 minus n2 into twice of n1. Can I write it that way? Because I have assumed that n1 is approximately equal to n2. So n1 plus n2 will be approximately equal to twice of n1 upon twice of n1 square. Okay. So this, so in the denominator I am left only with n1. So it is approximately equal to, delta is approximately, not exactly, but it is approximately equal to n1 minus n2 upon n1. So that's another formula for one very important parameter, that is delta, which is also called as the relative refractive index difference or index contrast between the core and the cladding. So this is one equation. This is very important equation. Let's say A, equation B, equation C. Now one more thing, let's say I want to find out the relation between numerical aperture and delta. So can I do that? Yeah, of course I can do that. Numerical aperture, we know that it is equal to this is equal to square root of n1 square minus n2 square, and delta, the formula for delta is equal to n1 square minus n2 square upon twice of n1 square. Okay. So take it as 1 and take it as 2. Let's say I am squaring both sides of equation number 1. So numerical aperture square will be equal to n1 square minus n2 square. Okay. And delta, I am replacing, this is 3, let's say. So put equation number 3 in number 2, in equation number 2. So delta will be equal to n1 square minus n2 square की जगह पे I am replacing it by n numerical aperture square upon twice of n1 square. Okay. So from here I can write down the relation between numerical aperture and delta, and it comes out to be numerical aperture square is equal to twice of n1 square into delta, or numerical aperture is equal to n1 into square root of 2 delta, taking square root on both the sides. So I got another relation, very important relation between numerical aperture and delta. Numerical aperture is equal to n1 square root of 2 delta. Okay. Now here I want to conclude. In this video I tried to explain the derivation of numerical aperture. We derived that the formula for numerical aperture is equal to square root of n1 square minus n2 square. We also said that it is equal to sine of the acceptance angle theta A. And then we talked about delta, that is relative refractive index difference, and that is equal to n1 square minus n2 square upon twice of n1 square. We also derived the relation between numerical aperture and delta, and that is numerical aperture is equal to n1 into square root of 2 delta. Now I want to conclude this video by saying that the formula for numerical aperture says that it is equal to sine of the acceptance angle, and it is also equal to the square root of n1 square minus n2 square, which simply means that the numerical aperture of an optical fiber is dependent on the refractive index of core as well as on the refractive index of the cladding. Okay, it is independent of the core and cladding diameter. Thank you so much. I hope this derivation is clear to you all. Thank you for watching.